Alright, hello everyone. We are, I think, pretty close to a year of uploading videos. Just got 2 more days. But yeah, let's keep it going. Yeah, minimum height trees. So here we have a problem where we're given a tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycle is a tree. Okay, given a tree of n nodes, labeled from 0 to 0 to n minus 1, and an array of n minus 1 edges, where edges of I denotes A of I to B of I, indicates there is an undirected edge between the two nodes A and B in the tree. You can choose any of the so you can choose any of the node of the tree as the root. When you select node X as the root, the result tree has h height. Among all the possible rooted trees, those with the minimum height are called the minimum height trees. Return a list of all the minimum height root labels. You can return the answer in any order. Okay. So we're given n. Okay, so we have a label. So for 0, 1, 2, 3. We're given 3 and 4 because they have the same height. Because 1, 2, 1, 2. Okay. Wait. 1. Okay, the height is the root to the longest one. So this is 1, 2, 1, 2, 1, 2. Yeah. I'm going to count height as the number of edges there are towards the root to the height. And we'll just pick a root. Okay. So I see a vision now. So maybe we do some DFS to calculate the height, because that'll be useful, right? Or we could do BFS to count the levels, how many levels that we have to traverse. This is 1 level, 2 level, 3rd level, 1, 2, 3. Actually, BFS might be nicer. I don't want to deal with recursion. So this is 1 level, 2 level, 3 level, 1 level, 2 level, 1 level, 2 level, 1 level, 2 level. Okay, so okay, I'm going through every single one from 0 to n minus 1. Call our BFS function, which just calculates how many levels there are. So 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. And so, okay, I have an idea. Okay, the problem is finding the smallest. So how can I find the smallest? The height of tree 1 is 1. 1 is the root with. Okay, so yeah. Okay, so I could do 1, 2. How do I want to calculate the height? I'm gonna do by level. So there's 3 levels. There's 1, 2, 3 levels here. So that's how we determine that. But the thing is, how do I score that? So I should probably have the smallest, so which is 3, and then so I should probably write I have to probably iterate it twice. One to calculate all the scores, meaning all the heights, and then a second loop to go through all the ones that have the smallest and add it to a result. Okay, so go through our list of. Let's first look at this. So we have here, create a graph, undirected graph. Create an undirected graph, go through each node as a root, starting from 0 to n minus 1, right? Then from here, go through each node as a as a root, starting from 0 to n minus 1. then calculate the height via BFS by counting the amount of levels. Calculate the smallest. Append, put roots where put roots where node is the put roots that have the small smallest levels. Okay, so that's a pretty straightforward plan. So let's get to it. So we have a graph here. We'll have a default dict list, and we'll do for every A, B in edges, graph of A equal dot append B. And yeah, that's pretty straightforward. And then we'll do def BFS. And basically the start, we'll call it a source. We'll implement that later, and then we're gonna do two things. So the smallest, which is gonna be float inf, and for every I in range, actually I'm gonna score levels, and we're gonna score them. So we're gonna go through 4 root in range from n, right? We'll call BFS root, and levels, we'll do the count, and levels dot append count, right? And then for every I in range, I guess we'll call this for every node, or for every okay, and res here, return res, and then for every I in range of n, levels. Okay, also actually now we'll have a smallest count here. We'll do it at the same time. Yeah, the smallest is some arbitrary number, so arbitrary large number, and we'll do smallest equals min of smallest and count. And then just for every I, we'll do res. Oops. For every I in range of n, res dot append I if levels of I equals the smallest. I feel like there's a better way to do this, but I can't really think of it. I don't know why. So yeah, basically that. And then now we do the source. So the source will give us some values here. It needs to return a count. So basically, we'll have the queue here. We'll use a dequeue, and obviously we'll start with the source, and then we'll while queue. Actually, we do need to do a scene. So I use a set here, and then for every I'll do while queue for every range of queue length of queue scene dot add Oh, okay. Cur dot. We'll do q dot pop left, right? Oh Lord, help me, God. I really need to get rid of this. Okay. Cur dot pop left. Scene dot add cur. And if cur in scene, continue. Or just don't add it at all. Well, yeah. Or how does this work? Yeah, if cur in scene, continue. And then, okay, and then for every time we do this, level count, we'll do this, and return the count. Okay, so now we do the add the thing, and then do for every neighbor in graph of cur, we'll add, if, yeah, actually don't we even add it if we haven't seen it, you know? No, we do need this. Yeah, I should prevent it from being seen in the first place. If neighbor not in scene, then we'll do q dot append neighbor, right? And every time we're done with the level, so once we process each level here, we'll increment our count here. So that's level 1, level 2, level 3. This is level 1, level 2. Yes. And yeah, this should be a kind of a reasonable idea. So idea is we create the graph, we create our BFS, we call the BFS every time for every single, I guess, node here. And yeah, let's try it. Okay. Let me just see what the smallest is actually. So the smallest should be 1. Okay, that doesn't make really any much sense actually. Actually, I'm gonna do one more because we're already on the first level, if that makes sense, right? So that might help a little bit of stuff. Okay, never mind. Did not. Okay, I actually don't understand what is happening. Smallest. Let's print the smallest. Oh God, this is really annoying. Smallest is, yeah. Well, I didn't want it to judge. No. Smallest is 2. Yes, that is true. Now let's see. Levels of I equal the smallest. That doesn't make sense. Huh? Print. What's going on here? Oops. I missing something? I don't know what's happening here. Print I. Wait, why is this iterating all weird? 0, 1, 2, 3, yeah. Oh, okay, now let me double check what's in levels. Am I just getting all 2s? Oh wait, I messed this up, yeah. So this is, oh wow, that's actually really weird, hold on. I might have done my BSS wrong. The score should be 3 here. 1, 2, 3. This should be 2. 1, 2. Okay, so my levels is calculated wrong. I don't know why. What's happening? Am I not calculating the levels? Scene.add cur. Oh shit. Wait, no, that's fine. For every neighbor in. Oh, I forgot to do the inverse because it's undirected. Yeah. That could help. Alright, there you go. This is too small. Yeah, that I feel like it would be really small. Yeah. How could we optimize this? How would I optimize this? So if n is super large, doing this is kind of a brute force. I got an idea. Maybe we can do an algorithm that counts the in degrees. This has an in degree of 1, 2, 3, 4. 1, 2, 3, 4, 5. Well, nah, the in degrees won't work. So this worked, but it's just too slow. Okay, let me see. Yeah, it's 2 times 10 so this is like an n squared solution, so too slow. But I think we should use the idea of like in degrees, because I think that's useful. Because like if we have like nodes like, let me pull up like if we have nodes like this, right? We have how many, what could be the possible one? It could only be one, right? If there's 2, right? There's 2, there's those 2. It could be 1 or 2, right? Because the heights are basically like either or, right? So we can put both. But if it's 3, then it's just the middle one, basically, right? The middle one, just 2, right? Because the height would be whatever the to minimize it, you take the middle one. So at most, the length of the result will either be 1 or 2. And it depends on if there's an even amount or an odd amount of nodes. Because if it's an odd amount, then you just take the middle one. If it's an even amount, then you just take the middle 2. So the idea is basically, okay, we can shave off, like if it's like this many, we just try to shave off how many these like nodes off until you get 1 or 2 left. Yeah, so like let's do a 4 count, so it'll be like this. Actually, no. Let's do like, okay, if there's 4 nodes, right? These 2 are the possible candidates, right? Either by like this, either like this, or like this, right? And basically we just want to shave these 2 off, and we like that. And I do need to count like an in degree, so let's actually have a degree here. Times n, yeah. Degree of A, degree of B, and we only want to consider those with degrees of 1s, and we only add them to our BFS when they have more than when they are equal to 1, when they at least have 1 to them. Because if they're not, then we want to keep them, because those guys are probably the one with the parent, right? Like, well, okay, not true. We keep taking them off until they are less than 2 nodes, because once there's 2 nodes left, like take 1 or 2 nodes, we'll take this guy off, boom, we got the 4, or it's mainly 3 and 4. We're gonna find them both at the same time, but we're gonna just have one tree, and then we're gonna have one tree like 4, right? Like this situation we got here, and then we just want to trim these off until we find the last 2, because you can form them as the thing. So yeah. Okay, so then we'll do nodes, or let's have a queue. We'll do a DQ, and we'll do for every I in range from n. We want to add only if I equal to yeah, no, that's fine. Okay, if I actually, yeah, let's do this. If I equal to 1, or actually if I degree of I equal to 1, yeah, only if they have somebody going to them, right? Then we'll do nodes, I guess, which is length of graph in a way. Actually, it's just n. There are n nodes. 1, 2, 3, 4, 5, 6. Yep, there are n nodes. While there are at least more than 2 nodes, right? If there's less than that, then we found either 2 or 1. So we're going to nodes, yeah. So we're gonna do for every I in range of length of Q. We're gonna actually decrement length of Q. We're gonna obviously do that. Yeah, that's how many nodes we're gonna get rid of. Actually, we'll just do nodes to 1 at a time. Okay, then for every neighbor in graph of Q, or graph of well, actually, I gotta do cur equals Q dot pop left, cur equals this, right? For every neighbor in that, if the degree of neighbor equals 1, then we add it to our Q dot append neighbor. Otherwise, cur will do degree of cur. We want to get rid of that, and then we'll decrement nodes every time and return the remaining nodes in our list. So list of Q. There's gonna be at least 1 or 2 left in the queue, so we just put that as a list. Okay, there's nothing in the queue. That sucks. Okay. Actually, I only want to do it if we add it to our queue. Yeah. No. Okay, so for every I in range, oh no, I meant to put neighbor here. So every time if it's one, then decrease that and then put it in our thing. And then now we do that. Now there should be only one or less. Okay, not quite. Yeah. Wait, let me. Yeah, nodes of. Yeah, it's fine. Nodes. Yeah, we're gonna do this anytime. So every time we use a node, we've used that many nodes. So we did that. Yeah, just get rid of those. How many nodes there are? What? Okay, is it maybe the? Hold on. Maybe I should get rid of the nodes. That makes no difference. I'm pretty sure, like, I'm supposed to only add nodes one at a time. Yeah, so that should work, I feel like. I feel like I should do it every neighbor there is, visit it, I guess, peel it off, and then if it's actually a 1, perfect. Then that's perfect. Then we want to add that to our thing. So like for example, we have like this here, like the in n degree here, right? We're gonna start from 0. 0 is here. I guess the neighbor is gonna be 1. Decrement that down. Is it equal to 1? No, so we don't add 1. Then, yeah, that should be it though. Yeah, there you go. So we go through the thing. 0 is here. And then, okay, yeah, that's done. So, yeah, 1 right now, it doesn't have anything. Then we go to the next one, which is going to be 1. For every 1, it has a bunch of neighbors, so we're going to do this one. That's going to take 1 away. This one is gone, so we trim this guy off. Then we go here, trim this guy off, and then we're eventually going to have a guy with this guy here, which is going to be the remaining nodes. It's still going to be in the queue. I think. Now, let me rethink this. So 0 goes here. Yeah, that should work. I think this works, yeah. Okay, never mind. Bro, okay, I'm hard coding that. If n equals 1, then return 0. Yeah, that makes sense because, like, if there's only 1, then the 0 has to be. Anyway, see you guys tomorrow.